Welcome, everyone, to this Applied Engineering Explainer. I'm your host, Dr. Ramani Bai, and I'm thrilled to be guiding you today alongside my brilliant colleague, Mr. Taha Muhammad Jassim, right here from UCSI University in Kuala Lumpur. Today, we're going to roll up our sleeves and break down something absolutely crucial, the Cube Compressive Strength Test for hardened concrete. I mean, it's literally the test that keeps our modern world from just collapsing. So let's jump right in, shall we?
Here's our quick roadmap for today's session. We're going to cover real-world concrete strength, mixing and casting concrete, the curing process, testing and calculating strength, and finally, limitations and quality control. Let's get to it.
All right, Section 1, real-world concrete strength. So let's establish exactly why this lab procedure is so fundamental. We really need to understand how this connects directly to modern industrial maintenance. Things like heavy-duty factory flooring and massive infrastructure safety.
The big, crucial concept we're dealing with here is compressive strength. Simply put, it's the concrete's ability to withstand axial loads that are actively trying to compress or squash it down. Just imagine the sheer, immense vertical pressure acting on a highway bridge pillar, or maybe a heavy-duty factory floor with massive machinery. If we mess up the mix and those inconsistencies go undetected in the lab, well, the structural integrity of that real-world infrastructure is severely compromised. No way we can let that happen.
And this brilliantly illustrates exactly where our data is coming from today. We're actually analyzing the precise measurements and procedures documented in Experiment 4.1 from our very own UCSI University workshop. We'll be focusing on a standardized structural concrete design, specifically an M25 concrete mix, just to see exactly how these strength parameters are proven in a strictly controlled environment. To quickly summarize this first part, just remember that the numbers we generate right here in the lab directly translate to the safety of the environments we walk and drive on every single day.
Moving right along to Section 2, mixing and casting concrete. Okay, let's step into the lab and break down the exact sequence for making our concrete specimens. Believe me, accuracy here literally dictates the success of the entire test.
Now, take a look at the single, very specific number, 0.60. For this experiment, our water-cement ratio is strictly locked in at 0.60. In concrete design, this ratio is kind of like the ultimate balancing act. You're constantly trying to balance the workability of the wet mix with the final structural strength of the hardened product.
This table details our exact formula. We're using a 1:1:2 mix proportion, yielding exactly 0.007 cubic meters. Look at the absolute precision required here before we even think about turning on the mixer. We need 2.52 kilograms of cement, 2.625 kilograms of sand, and 2.45 kilograms of coarse aggregate. And to hit that strict 0.60 ratio we just talked about, we need exactly 1.512 kilograms of water. Not a drop more, not a drop less. So, with all our materials weighed out, we follow a very strict operational sequence. Try to visualize the rotating drum of the mixer. The dry aggregate, sand, and cement, they go in first. We dry mix them for about 1 minute just to really blend those particles together. Only then is the measured water gradually introduced into the rotating matrix. We let it mix for 2 more minutes until we get this beautifully uniform consistency, with absolutely no dry cement pockets left behind.
Next up, the concrete is cast into our standard 150 millimeter cube molds, and we do this meticulously in exactly 3 layers. First, fill the mold 1/3 full, then compact it with a tamping rod exactly 25 times to force out any trapped air. Repeat that whole process for the second and third layers, and finally, level the top so it's perfectly flush. So, wrapping up this phase, precise ratios, sequential mixing, and layered, well-compacted casting, those are your keys to a perfect specimen.
All right, Section 3, the curing process. After casting, our concrete has to undergo curing. This is a totally non-negotiable step to activate the chemical hydration of the cement.
So, the freshly cast cubes are left completely undisturbed for 24 hours. After this initial set time, we demold them, mark them up, and then completely submerge them in a curing tank. The water maintains the continuous moisture needed for the cement to hydrate, which allows the internal matrix to become much, much denser. Actually, think to yourself right now, what would happen if the water temperature in that tank drastically fluctuated? Well, it would alter the hydration rate entirely. It's that sensitive.
But before we look at the final numbers, let's test your understanding of proper lab technique. Here's a quick knowledge check for your assessments.
What actually happens if our concrete is placed with inadequate vibration during that multi-layer casting stage we just talked about?
Well, if you guessed internal structural flaws, you hit the nail on the head. Without proper compaction, trapped air voids just sit there inside the block. These voids act as major weak points that will drastically reduce the concrete's ability to withstand pressure. That compromises our test, and in the real world, it compromises the building itself. So wrapping up Section 3, proper casting and consistent water immersion are your absolute pillars for successful curing.
Okay, moving to Section 4, testing and calculating strength. This is the fun part, where our cured cubes finally face the universal testing machine so we can analyze the actual results.
To find our final values, we use the standard engineering formula you see right here, FC equals P over A. So, the maximum applied failure load, which is recorded by the machine in kilonewtons and represented by P, is divided by the specimen's loaded surface area, which is A. For our standard 150 millimeter cubes, that area is 22,500 square millimeters. Doing this simple division gives us our compressive strength in megapascals or newtons per square millimeter.
Our raw machine data translates directly into actionable engineering insights. Just look at the jump in these results. Cube 1, which was tested after just 7 days, sustained a failure load of 55.11 kilonewtons, resulting in a strength of 5.511 newtons per square millimeter. But Cube 2, given 14 days to cure, it sustained a massive 186.54 kilonewtons, achieving a strength of 8.291. This chart brilliantly illustrates the chemical realities of concrete. As you can clearly see, compressive strength significantly increases with extended curing time. It's a perfect demonstration of that ongoing hydration process we discussed. The longer the cement matrix interacts with water, the stronger it gets, plain and simple. So to sum up our testing phase, precise area calculations combined with extended curing time yield exponential strength gains.
Section 5, Limitations and Quality Control. To truly master this procedure, as future engineers, you have to critically analyze the limitations of the testing environment itself.
We absolutely have to recognize what can skew our data. For instance, imagine the internal stress distributions during crushing. Variations in a specimen size or shape, they're going to alter those stresses unpredictably. Furthermore, the rate of machine loading is absolutely crucial. If the machine applies pressure too fast, it's going to artificially inflate the strength reading due to lower material creep. The load must be applied continuously and, most importantly, without shock.
To mitigate these field errors in your own lab practicals, you must rigidly adhere to these key quality control precautions. You need to ensure uniform mixing without material segregation. You have to execute proper vibration to eliminate those dangerous air voids. Always utilize accurate mold dimensions, ensure axial loading at the specified rate, and please, always verify the regular calibration of your testing machines.
Okay, let's review what you really need to take away from this explainer. As you prepare for your final assessments, lock in these core summary points. Our experiment utilized a 1:1:2 mix proportion with a strict 0.60 water to cement ratio. Now ask yourself, how did we verify workability? We confirmed it with a 45 millimeter slump test. And finally, our crushing data verified that compressive strength increases steadily from 7 to 14 days of curing.
I want to leave you all with a slightly provocative final thought. While this localized lab test successfully proves compressive strength, how do we account for long-term durability, tensile strength, and severe environmental exposure when we're building massive real-world construction projects? It's a vital question to consider as you step out of the laboratory and into the field. Because true engineering mastery, it requires understanding the whole picture. Thank you so much for joining me for this session, and keep exploring the mechanics of our world.